So chapter 12, we started talking about bonding, and we really talked about a couple of different types of bonding. We talked about ionic bonding. And ionic bonding, as we talked about, is always between a metal and a non-metal. And remember that because of really the differences, or kind of the big differences in their periodic trends in terms of how they sort of deal with electrons, where metals typically don't really want to hang on to them, while non-metals really want to sort of gain them. What we end up getting when we have this occur is a transfer of electrons from the metal to the non-metal. The result of that is we will form a couple of ions here. We'll form our cation, which is from our metal. And that is our positively charged ion. From our non-metal, we'll form our anion. And remember, one of the important sort of aspects of ionic bonding is there really is no sharing of electrons. So what is holding that together is basically the opposites attract, or the electrostatic attraction. And that is really different than what we see with covalent bonding, which is really the other type of bonding we talked about. And in covalent bonding, it's always between two nonmetals. And because basically both nonmetals are hanging out there on the periodic table in the same exact spot almost, they all have also very similar periodic trends in terms of they really both want to hang on to their electrons. They're not really willing to give away their electrons. So the best that they could kind of come up with when two nonmetals get together is a sharing of electron situation. So unlike ionic compounds, here we do have sharing of electrons. And as we talked about, the sharing really falls into sort of two categories. One is a polar covalent bond. And in a polar bond, we have unequal sharing of electrons. And the other sort of category is a nonpolar bond, or nonpolar covalent bond. And there we have equal sharing of electrons. And what really is sort of the overwhelming sort of determination as to whether or not those electrons would be shared equally or not is electronegativity. So it really is that electronegativity that we talked about. Remember, on the periodic table, electronegativity increases as you go that way and decreases as you go down, with fluorine being the most electronegative element you could have. And what we look at is sort of the electronegativity values is one way that we can look at it. And remember that those values run from 0 to 4, with 4 being the most electronegative. So if you have a difference in electronegativity value of anywhere from like 0 to 0.4, that's considered a nonpolar bond. And we would expect that the electrons would be shared equally in that situation. Anywhere above 0.4, so we'll call it 0.5-ish, I guess, and above, to below 2 is some type of polar bond. And that basically would mean that we would expect the electrons to be shared unequally. And typically speaking, but not in all cases, as we talked about last time, anything typically above 2 is an ionic bond, which we would have no sharing of electrons basically occurring. Remember, we did talk about a couple of things that if you happen not to have the actual electronegativity values available to you, you could use pretty much the general trend of electronegativity on the periodic table to probably make a fairly reasonable guess as to whether or not you would expect it to be a polar bond or non-polar bond. Remember, not all sort of metals and non-metals will give you that 2 or more difference, but one thing that you do know for sure is, in this class for sure, and all chemistry classes that you take, if you have basically a metal and a non-metal together, it should be an ionic bond. You really don't even need electronegativity values to tell you that. It's a pretty safe bet just to, know that it is ionic when you have that metal and non-metal together. The result of guys that are polar or non-polar, you can also use the general trend in electronegativity to make a good guess. If somebody is in the same row on the periodic table, they should be more electronegative if they're further to the right. So if you're comparing two atoms that are in the same row on the periodic table, it's a pretty safe bet that you are going to have a big enough difference in electronegativity value when you're dealing with nonmetals that it will be a polar bond. So even without the numbers, you could pretty much guess it's going to be polar. Also in the same group in terms of nonmetals as well. If you have two elements that you're comparing in the same group, you could also make a fairly educated guess that it's probably going to be a polar bond, with obviously the element that's further up in the group being more electronegative. And even without the numbers, you can make a pretty good guess. The other result of this sort of unequal sharing of electrons that occurs with polar bond is we could represent that by a dipole arrow. And remember, the arrow always points to the more negative side of the bond, or the one that's more electronegative. So in this case, fluorine should be more electronegative, so it would point towards fluorine. And again, the back end of the arrow that makes like a plus sign is sort of the one that's more positive or least electronegative. We also could represent this as partially negative and partially positive charges develop within a polar bond. And remember that, as we talked about last time, they're still they're called partial positives and partial negatives because there is still some aspect of sharing of the electrons going on. There hasn't been a full transfer of electrons like we see in ionic compounds, where we would have full pluses and minuses sort of made. We also talked about drawing Lewis structures for ionic compounds. And remember, when you draw something that is a Lewis structure for an ionic compound, you do need to include the charges to indicate that there is no sharing of electrons there. And usually, as we talked about, sometimes you'll put a bracket around, the negative guy or all the ions that are present. But again, when you do draw those Lewis structures, that's how you do it. The Lewis structures contain the valence electrons, which is equal to the group number. So again, that's how you quickly can figure out how many valence electrons everybody has. It does equal the group number. Any questions on that there? And most importantly, as we talked about last time, the real whole purpose of any type of bonding, be it ionic bonding or covalent bonding, for everybody to achieve the same electron configuration as the noble gases, right? That's the basis of the octet rule and the duet rule there for hydrogen. And that is a very stable sort of configuration. With ionic bonds, they do it by losing electrons and gaining electrons. In covalent bonding, they do it by actually sharing of electrons to allow everybody to kind of reach that noble gas configuration. Any questions on any of that stuff we talked about last time there? Okay, so to continue on here, I think it's somewhere where we left off. So as we talked about, again, ones with widely differences in electronegativity, and again, metals kind of left the periodic table, non-metals upper right, they tend to have that transfer of electron ionic bond happening, while again, everybody sort of in the non-metal region and a covalent bond is very. We also talked about the idea that in terms of electronegativity, there sort of is a diagonal rule that can kind of occur. And I think we saw an example of that as well. It is possible to have two different elements that has the same electronegativity value. So I think maybe we did. And you can get a difference of 0 in terms of it. And again, as we talked about, they have sort of that diagonal relationship on the periodic table, like nitrogen and chlorine as well. One is further up, but one is further to the right. So they sort of cancel out their differences and they end up with the same electronegativity value. So it definitely is possible to have two different elements that could be a nonpolar bond. For 100% of the time, if you have two elements that are the same, obviously, I guess you went two atoms that are the same element. It's a better way of saying that. If you have two atoms that are the same element, they're definitely going to be nonpolar. But in terms of general trend and using it for electronegativity values, that's really the only thing you should keep a watch out on, is sort of that diagonal relationship that happens up there in the non-metal region. So obviously our ionic bonds and our covalent bonds. Now, sometimes people will talk about bonding in terms of percent ionic character, and really not too much these days. People don't really talk too much about it, but we'll talk this a little bit here. Sometimes they do refer to bonding as percent ionic character, where 100% is pretty much all an ionic bond. 0% is really a non-polar covalent bond, and obviously polar would be somewhere in the middle of those two percentages. Most people just nowadays talk polar, non-polar, ionic, but occasionally sometimes people talk a little bit about percent ionic character, and that's basically what it means, as we can kind of see in this diagram here. We have two of the same atoms of an element, which means they're going to share it equally, which means 0% ionic character, which basically means it's a pure covalent or non-polar bond. Over here, this is 100% ionic character, over from the sodium to the chlorine. And obviously our guy here, which would be a polar, would be somewhere percentage-wise in the middle of those two. Again, depending on the degree of sharing or unequal sharing that we saw. We've talked about sort of how we could determine whether or not we have a polar bond. And we talked about earlier on in this chapter how to draw Lewis structures for ionic compounds. What we're going to be talking about here is really the good way or the proper steps to draw Lewis structures for covalent compounds. So everybody's sharing electrons here. If you follow these steps, you really should end up with a pretty good picture. I won't say it's the perfect picture 100% of the time, but a pretty good picture. If you do not follow these steps and you do like a lot of people do, which is, I sometimes call it piecework, like they draw all the individual elements with their valence electrons and try to figure out where everybody sort of goes. A lot of times you'll end up with wrong number of bonds, too many electrons and stuff like that. So if you follow these steps for covalent compounds, it's really a good way of getting that good picture at the end. And it's a little bit different than how we do it with ionic compounds. So the very first thing that you want to do when you're thinking about drawing a Lewis structure for a covalent compound is you want to think about sort of what's sometimes referred to as the skeletal arrangement. So there's sort of the logical arrangement of how all the atoms are sort of put together. I will say a lot of things that you draw in most of your chemistry classes will have kind of like one central atom and then everything else is attached to it. It's not always the case. You can have multiple central atoms with a bunch of things sort of attached, but more times than not, you're going to have that sort of one guy in the middle and everybody attached to it. So how do you know who should maybe go in the middle and who can go on the outside? So the general rule that you should follow when you're drawing Lewis structures is typically the least electronegative atom is in the center. So again, the one that has the least electronegativity is usually the guy in the middle. That means that we will never find hydrogen in the middle because hydrogen should have how many electrons? 2 and only 2, which means if you put it in the middle, it's going to have way too many electrons to it. A reminder and a good reminder that pretty much in your pictures, that's what hydrogen should look like on the outside. There should be no dots, as we talked about last time, no triple bonding, double bonding, or anything like that. That's essentially what hydrogen should always look like. So again, if you find yourself having the urge to put dots around hydrogen, don't do it. Yes. The other thing that you shouldn't do is fluorine in the middle, as fluorine is the most electronegative element. So clearly that would not be the least in a situation. So we typically never find hydrogen or fluorine in the middle. Least electronegative is in the middle. And again, more times than not, one guy in the middle, everybody attached to it, but not 100% of the time. Maybe we'll look at an example as we come through this. Probably the most important thing that you do when you draw a Lewis structure is actually count up the number of valence electrons there are. Now, we want to take all the atoms that are there and all the elements that are there and count up just a grand total of all the valence electrons that are available. Again, using the group number as the number of valence electrons for each element. We also need to take into account if we do have something that has a charge. So if you happen to be drawing something that's a polyatomic ion, which is a guy that's a bunch of nonmetals that have charges, you do have to take the charges into account on your total for your electrons. So if something has a negative charge, that means that it has gained electrons. So you need to add that number to your grand total. If somebody has a positive charge, that means it has lost electrons. So you need to subtract that from your total. Otherwise, you're going to be too short or too many electrons in a situation. Now, that is probably the most important thing, because when you're done with your picture, you got to hit exactly that number on the nose. You can't have any more or any less electrons. It's got to be exactly that. And this is the thing that most people kind of run into trouble. We want to think about the electrons as available to everybody, not necessarily belonging to the nitrogen or belonging to the oxygen. It's like we got 26 electrons. We need to kind of distribute it out to everybody as equally as we can. And that's a good way to think about it as you're drawing these pictures. Is sometimes people go, well, nitrogen had 5 and this guy had 7. So shouldn't they have, get this many and that? You want to think about the electrons as sort of not really belonging. That you want to do is, once you figure out sort of the logical arrangement and how many electrons your picture should have, you want to make one single bond from the central atom to each of the outside atoms. And personally, I use a line to represent that bond. If you want to use dots, you can, but remember, one line represents 2 dots. So for bonding, I personally use a line to do that. Once you take one single bond to the outside atoms, you would have used up a certain number of electrons. You want to look at your total number of electrons and figure out how many electrons you have left. Whatever electrons that you still have left to put onto your picture, they should first go to the outside atoms in pairs of electrons, as in dots on the outside atoms is how they should go. And you should fill up all the outside atoms as pairs of electrons until every outside atom has 8 electrons. And if you do that, and you filled up everybody, obviously with 8, except for hydrogen, it should only have 2, and you still have electrons you need to put on your picture, then you go to the center atom and you put those on as dots as well. So the idea here is a single bond from center atom to each of the outside atoms, pairs of electron on all the outside atoms until they're full. And if you still have electrons, central atom gets pairs of electrons as dots. You definitely do not want to, in most cases, double bond and triple bond right out of the box, thinking it looks more scientific-y or chemistry-y. That's not usually going to give you the right picture. So we want to think about in this class probably saving double bonds or triple bonds for a situation where somebody does not meet the octet rule. And that's the last thing that you want to do, which is after you've sort of assigned all the electrons that you should have in your picture, you want to go back and make sure each element in there or atom in there has 8 electrons, except for hydrogen, which has 2. And it's at that point, if somebody does not have 8 electrons, you want to try to fix it. And the first way that you would want to try to fix it is actually to try to make double bonds. And if the double bonds fix it, you're done. If it doesn't, then you need to make triple bonds. So that's sort of the order as to how you want to do it. You want to kind of single bond everything up. And then if it doesn't meet the octet rule, try to fix it with double bonds. And if double bonds don't fix it, then try to fix it with triple bonds. Any questions on any of that? All right, so let's do one together to see how we put all this together and do it. All right, so we want to draw the Lewis structure here for nitrogen trifluoride. So the first thing I'm going to do is count up the total number of valence electrons. So I go to the periodic table, nitrogen's group number 5, which means it has 5 valence electrons. There are 3 fluorines, each fluorine's group 7, which means they have 7 valence electrons. It's like a 26 valence electrons. So that number is really important because when I'm done with my picture, that's pretty much where I got to hit exactly that number. Now, between nitrogen and fluorine, which one should go in the center? It should be nitrogen. Just in terms of electronegativity, if you look on the periodic table, they're in the same row, and fluorine is the most electronegative furthest to the right, and that means that nitrogen should be in the middle. I would also say in most cases, if you have one element like nitrogen, just one atom of it, and some other elements, usually the one that's the one atom is the guy in the middle in most cases. So we're just going to take a logical way to arrange this, which is nitrogen in the middle. We're going to put the fluorine on some sides here. And again, I put the fluorine on the bottom. You could put it on top. It doesn't really matter. I personally kind of think of it as the same four sizes we kind of talked about earlier, and, kind of spread them out to each side. Now that I have my logical arrangement here, the next thing I'm going to do is just to make one single bond from the central atom to each of the outside atoms. And I'm going to figure out how many electrons I just used. So each of those lines represent 2 electrons, and there's 3 lines, which means I've just used up 6 electrons. If I subtract that from my original total, I still have 20 electrons that need to be put onto my picture. 20 electrons are going to go on as pairs of dots. So not 1 dot at a time, but 2 dots at a time. So you want to pair them up and put them on that way. We're going to put them on the outside atoms first. So we're going to do a 2, 4, and 6, and that guy is full. 8, 10, 12, that one is full. 14, 16, 18, and that one is full as well. At this point, I pretty much filled up everybody on the outside. The grand total of electrons I've used so far is 24, which means I still have 2 more electrons I need to put on my picture. So since everything on the outside is filled, the only other place to put it now is to the center atom, and it also goes as a pair of electrons like so. And now I have placed 26 electrons on my picture. The last thing I want to do is just to double check everybody's good in terms of electrons. So fluorine on the right has 2, 4, 6, and 8 electrons. This fluorine 2, 4, 6, 8, 2, 4, 6, 8. And now if we look at the nitrogen here, it has 2, 4, 6, and 8. So everybody has 8 electrons, and that would be the correct Lewis structure without all the highlighting, as to what you should draw. Any questions on any of those steps? If you follow those steps, like I said, it should lead you to the correct picture every single time. Again, don't try to put it together piecewise. Any questions? All right, I tried one, you try one. There you go. That's the one I just tried. Hopefully it comes up the same. That's good. All right, why don't you give this one a go, see what you come up with. This is nitrate, which is NO3 minus. So this one has a -1 charge. You need to take it into account. Kind of see what you come up with. Try to follow those rules and see kind of how you're doing. So again, we'll start the same way. We're going to really count up the total number of valence electrons. That's kind of almost the first thing you want to really do. Once again, here we have nitrogen, which means 5 for the nitrogen, as it's group 5. There are 3 oxygens. Each oxygen is group 6 from the periodic table. And now we have a -1, which means it has gained an electron. So we do need to add that into our total here so that we end up with the right number of electrons. It's a lot of math. It's 18, 19, like 24-ish, give or take. Math wasn't my thing either. It's okay. 24 valence electrons. All right. So in this case, between nitrogen and oxygen, who should go in the middle? Should go nitrogen. Again, based on electronegativity, they're in the exact same row in the periodic table. Nitrogen is further to the right, which means it's more electronegative. And also, again, there's only 1 nitrogen, so that kind of helps. So we're going to do a nitrogen in the middle. Again, you can put the oxygens around whichever way you want to go. We're going to do a single bond to each of the oxygens. Once again, that has used up 6 electrons. So if I get rid of that 6, I think I got 18 left to go here. Once again, they're going to go on the outside in pairs. So we'll do 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, we have put onto our picture all 24 electrons. Is all of the atoms good here? They're not, and it is the nitrogen that's a little short. So the nitrogen actually only has 6 electrons around it. All the oxygens have 8. So again, if we look at our nitrogen, it's got 2, 4, and 6 electrons, and that's it. So we do need to fix it. Remember, everybody needs to have 8 except for obviously hydrogen. Can I just lay me up a couple of dots there. I cannot do that because now how many total electrons do I have? I have 26, which is too many. So you can't just put the dots in there to kind of fix it or anything like that. So this is a situation, as I was talking about earlier, where it is a situation where we want to kind of try to maybe fix it with a double bond. So we do want to make a double bond. In this case, each of the oxygens are identical to each other. They're all equivalent, they're sometimes referred to. So you really can make a double bond at any of the oxygens. Can I just lay me up a double bond like that? I can't, because same reason. I got now 26 electrons. The oxygen on top has way too many electrons at 2, 4, 6, 8, 10. So when we actually do go to make a double bond, or actually even a triple bond, what we're actually going to be doing is taking a pair of electrons and bringing them in to kind of make the double bond. So if I do that, I'm going to bring those pair of electrons in to make the double bond. And now I will have a double bond up there on top. We'll have my single bonds here on the sides. And because it does have a charge, we typically do put brackets around it with a little charge there on the outside. Now, if we look at it, each of the oxygens have 8 electrons. And the nitrogen also has 8 electrons. So again, our 2, 4, 6, 8. Guy on the left is the same. 2, 4, 6, and 8. And for our nitrogen there, it has 2, 4, 6, and 8 electrons. So everybody now has 8 electrons. We still only have a grand total of 24 electrons in our picture, and this would be a correct Lewis structure for nitrate here. Again, without all the highlighting. Any questions on that? Now, let's say you decided to double bond to the left, which is perfectly fine to do. So you decided maybe to do the double bond over here. Your picture would look something like this. Or if you decided to double bond there to the right, your picture would look something like this. And all 3 of these pictures would be acceptable. They're also related to each other. These are what are referred to as resonance structures. And resonance structures oftentimes happen in this sort of situation where you have pretty much options as where you could put the double bond. You could put it to the left, could put it to the right, could go to the top. And they create 3 Lewis structures which are equivalent to each other. And the real reason for that is the double bond electrons are what are referred to as being delocalized, which means they're actually moving around. So in certain situations, if you just kind of look at nitrate, we may find our double bond electrons up here, over here, or maybe over here. So those double bond electrons are really just moving around from one oxygen to the next. So the real structure is probably somewhere in the middle of all 3 of those. So you could draw all 3 structures as resonance structures. Resonance structures are usually separated by this arrow that heads in both directions. If you are asked to just draw a Lewis structure for a compound like this, any one of the 3 is perfectly fine to draw. If you're asked to include all the resonance structures, you should draw all 3 of them. Yeah. Any questions on that? I would say, again, in most cases, it's that double bond really where you kind of have that option. All right, so let's try some here. Why don't we do a few just to make sure? Why don't you draw CO3 2 minus? Why don't you draw N2? Why don't you draw CO2? Why don't you draw H2S, NH4 plus? Why don't you also draw why don't you draw nitric acid? And I'll kind of tell you how that's connected. So nitric acid is connected. There's actually a hydrogen that's attached to a oxygen. So it looks something like that. All right, so take a few minutes or so, draw up some good Lewis structures for each of these. Then we will talk about them. So once again, what we want to do is count up how many total valence electrons. There are 2 hydrogens. Each one should be 1. And there's sulfur, which is 6. And that means that we should have a grand total of 8 valence electrons here. In this case, sulfur should be in the middle because hydrogen should never, ever find itself in the middle. So sulfur should be in the middle. We should have hydrogens on either side would be good. And again, we're going to follow the same procedure here. We're just going to make one single bond to each of the hydrogens. That has now used up 4 electrons. We have 4 more to go. Can I put any dots on the hydrogen? No dots on the hydrogen. So pretty much because they're hydrogen on the outside, they're all filled. So now we then proceed to the center atom, and that is where I'm going to put my dots. So we're going to do 2 and 4. That now has 8 total electrons. The sulfur in the middle has 8 electrons. The hydrogens on the outside have 2. That would be the correct structure there. Yeah. Any questions on that one there? Coming to nitrogen, which is N2. In this case, that's 2 times 5, which is nitrogen. And that would be 10 valence electrons in this picture. In this particular case, this is a diatomic molecule, which means there really is no center atom. So you can just set them side by side is the best way to do it. So we're just going to put our 2 nitrogens in this case next to each other. And even though there's no central atom, we're just going to do the same procedure. We're going to connect them with one single line. So one single bond to connect them. That still counts as 2 electrons, which means I still have 8 more to go. And we're still going to do the same thing. We're going to put those on one and then kind of work our way to the other nitrogen. So that's going to be 2, 4, 6, and that one's filled, and 8 at this point. So now I put on all 10 of my electrons. Are both nitrogens good? Now, the one on the left only has 4 electrons. So this is a case where we're going to try to fix it by first making a double bond. So just like we did on the previous slide, we're going to take a pair of electrons from the nitrogen on the right, and we're going to bring it in to make a double bond. And when we do that, we will end up with a picture that looks like this. Did that fix the nitrogen on the left? It did not. It got better. It's now up to 6 electrons, but it's still short. So there's obviously no place to make any more double bonds. So at this point, we then need to go to a triple bond. And a triple bond works the same way. We're going to once again take a pair of electrons from this nitrogen that has enough, and we're going to bring it in so that they'll be shared as well. And we will end up now with a triple bond between the nitrogens. And we still have our non-bonding electrons there. Now we are good. The nitrogen on the left has 8. The nitrogen on the right has 8. And we still only have a grand total of 10 electrons in this case. Any questions on that? Yes, sir. What's the? You do because if you're asking more, is there a difference between? Is that kind of like that guy and that bottom one? Yeah, so remember they then both wouldn't technically be happy because they really want to get to 8 each of them. So the only way they could get to 8 in this case is to share that triple bond. Because remember, as we sort of talked about last time, basically all those electrons in the middle count for the nitrogen on the right. So that technically gives the guy on the right 2, 4, 6, 8 electrons. But those guys are now being shared, and because they're being shared, they actually count for both nitrogens. And that allows the nitrogen on the left to also share those electrons and end up with basically 2, 4, 6, 8. So you do need the bonds to indicate that they're going to be shared. And that's really the only way that both of those nitrogens can get to that 8 electrons, which is what they need. Other questions on that? And again, that is again why nitrogen does end up with that triple bond. It allows everybody to get to that sort of noble gas configuration of 8 electrons. All right, looking at CO2, carbon is group 4, and there's 2 oxygens, which is 6, and that's a 16 valence electrons here. Once again, carbon and oxygen are in the same row on the periodic table, with oxygen being further to the right, which means carbon should go in the middle because it's the least electronegative. So because carbon's the least electronegative atom, we'll put it in the center. We'll do our oxygens on the outside. Once again, we're going to do 1 single bond to each of the outside atoms. That uses up some electrons, 4. We then have 12 more to go. So that's going to be 2, 4, 6, 8, 10, and 12. At this point, we have put on all 16 electrons. Is all the elements okay? Atoms. The carbon is not okay. It actually, again, here has 4, so it is short. So we're going to try to make a double bond to fix it. In this case, we can make a double bond on either oxygen. So I'm going to double bond first here to the left by bringing this guy in. And when I do that, I end up with a double bond here on the left. Still a single bond here on the right. Did that 1 double bond fix the situation? It did not. It got it better. Carbon's up to 6, but we're still short. Now, in this situation, you may be tempted to go, all right, I'm going to triple bond it over there on the left, which you could, but there still is an option to do a double bond on the right. And you usually want to sort of go through all your options. So you want to run through all the possible double bonds you could do. And if that still doesn't fix it, then you want to go to triple bond. So here I would not triple bond here because I could still double bond on the right. And that is what I would do. I would make a double bond on the right-hand side, again, by bringing those electrons in. And that will give me a double bond on both sides. And now I have 16 electrons. Everybody now has 8 electrons, and that is really the right structure. Could you jump to the triple bond on the left? You could have, but it's actually a worse picture than what we're looking at right now. It's actually a better structure is what you see here. So usually if you kind of follow that process, I don't have 8, I'm going to double bond, use up all your possible double bonds if necessary. And if it still doesn't fix it, then you roll into triple bond as sort of your last resort. The triple bond should definitely fix it, hopefully, in that case. Any question on any of those 3 Lewis structures there? All right, I'm going to flip the page and do the bottom 3 on the next page. Just have a little bit more room. We will start with CO3 2-. So in this case, we have carbon, which is 4. We have 3 oxygens, which are 6. And here we have a -2 charge, which means it has gained 2 electrons. So I do need to add those 2 to my total. And that's 18, 20, 24 valence electrons here. Once again, carbon is going to go in the center, oxygen on the sides. We're going to do a single bond to each of them. That is 2, 4, 6, leaving us 18 to go. So here we go, filling up the outside. 2, 4, 6, 8, kind of ran out of room here on the side. 10, 12, 14, 16, and 18. That now is 24 electrons. And hopefully, as you can see, we are a little bit problematic there on the carbon. It has only 6 electrons. Doesn't matter in this case where I lay up I'm going to spit that out and try that again. Doesn't matter where I lay up my double bond in this case. It doesn't, all the oxygens are equivalent to each other. They're all basically the same. So I'm in this case going to double bond up the top. And that's going to give me my double bonded oxygen up on top. Will give me still my single bonded oxygens on the left and right hand side. And once again, because it does have a charge, some brackets around it with a -2 charge. This is also another one where you could draw several resonance structures for. You could have double bonded there to the left, which would give you this structure. And you could have double bonded to the right, which would have gave you this structure. So once again, kind of like the nitrate here, we could draw 3 resonance structures for carbonate. And again, if you were just asked to draw a Lewis structure, you could lay up any one of the 3 pictures, you're good. If again, you were asked to draw all the resonance structures, you should draw all 3 of those pictures. Any questions on that there? All right, next one was NH4 plus, I believe. So in this case, nitrogen is group 5. There are 4 hydrogens each at 1 each. And now with the plus, what should I do? Add or subtract? Yeah, plus means it lost electrons. So we do need to subtract 1 from our total here. And that's going to give us 8 valence electrons. Nitrogen definitely going to be in the middle here because hydrogen clearly cannot. So we're going to do a nitrogen in the middle, a hydrogen on the 4 sides, 1 on each side. We're going to connect with a single bond. That is 2, 4, 6, 8. I am out of electrons, and I am good at this point because each hydrogen has 2, and the nitrogen has 8. So that would be the correct structure in this case. Any questions on that one there? All right, the last one that we were looking at there was nitric acid. So nitric acid here, which is HNO3. 1 for the hydrogen, 5 for the nitrogen, and 3 times 6 there for the oxygen gives us 18, 19, 24 valence electrons. In this case, you might not know how this is connected, but it does have multiple central atoms. We have an oxygen, a nitrogen, an OH, which makes it, that's what makes it an acid right there. So this is the logical arrangement. And again, if it is something like this, I would obviously give you sort of the skeletal structure here. And even though it has multiple central atoms, in this case, the nitrogen here and this oxygen here are considered central atoms. So it has 2 central atoms. We still do the same approach. We're just going to connect everybody up with a single bond. So we're just going to draw a single bond to everybody here. I'm going to erase my little scratches underneath so that we don't think there are electrons here. I'll get rid of that for now. There you go. All right. At this point, we want to count up how much we've used. So that's 2, 4, 6, 8 electrons. That means I got 16 more to go. We're going to do the same thing. We're going to work on the outside and then come in. So we will put dots on hydrogen or no? No. So then we will come over here to the oxygen on the outside. 2, 4, 6, 8, 10, 12. The next outside one is the other oxygen that could take some electrons. 14 and 16. At that point, I have now placed all of my 24 electrons. Is all of the atoms okay? Yeah, we are short here at the nitrogen. It has only 6 electrons around it. So we're going to make a double bond. Probably the only place you probably wouldn't lay up a double bond is over here, because that OH is really what makes it an acid. That's the hydrogen that comes off when it is an acid. But we can make a double bond at either the oxygens on the left. So we will do the same process we did before. We're going to take a pair of electrons here and bring them in. And when I do that, I will end up with a picture that looks something like this. And because you could also double bond on the left, you could actually draw a resonance structure for this one, where you do double bond on the left there. leaving the top guy a single bond. And either one of those pictures would be nitric acid. And again, it's that hydrogen that actually comes off that makes it an acid. We'll talk about it actually in a later chapter. Question on how to draw Lewis structures. Yeah. So again, you definitely want to kind of follow those steps. It will lead you to the right structure. Do not try to do a piecework or anything like that. Clearly, you need to be able to draw correct Lewis structures. You need to be able to draw resonance structures. Any questions on any of it? All right. And again, do not double bond and triple bond right off the bat. All right. So that one we just did. So we talked about resonance structures, but let's also talk a little bit about bond length. So this is a table of bond length, which is the distance between the two atoms in a bond. And he by no means has to memorize any of these numbers. But if we look at the carbon-carbon single bond, double bond, and triple bond, it's 154, 133, and 120. We look at the carbon-nitrogen, single bond, double bond, and triple bond. What we see is it goes from 143 to 138 picometers to 116. Here is every time we put a bond on and bring those electrons in, it brings everybody closer together. So when we pop a double bond, everybody gets closer. Pop a triple bond, the atoms get closer to one another. So every time you kind of bring those electrons in to be shared between them, there's more electrons in the middle. Positive guy is going to bring everybody in closer to each other because of that opposite attraction. And there is a relationship between bond strength and length. So a single bond is longer than a double bond, and that's longer than a triple bond. And that is how the strength works as well. A triple bond is actually the strongest, followed by a double bond, and the weakest of all bonds is a single bond. I think of it like a pencil, right? If you take a brand new pencil out of the box, you have no problem snapping that thing in half, right? If you take a chemistry test and you got like a nubbin less of an eraser, it's like that big, it's super hard to try to snap it in half, right? Everything's too close together, being held tighter. And that's what happens with our bonds. As the double and triple bond brings everybody closer together, there's a much stronger attraction holding that together, and it's a lot harder to break. A triple bond is not like 3 times as strong as a single bond or anything like that, but just the general trend is triple stronger, double next strongest, and the weakest would be a single bond. Any questions on that there? Now, we talked just a minute ago here as we were drawing our structures about resonance structures. And again, they are usually separated by that arrow in both directions. And again, it results really as a situation where you have more than one option as to where you can really place that double bond. So how do you figure out how you draw all your resonance structures? It's really wherever you can move that double bond to draw a new picture, you could do that. And that will give you that double bond. Like we just saw with carbonate, where we could have double bonded to the top, but we could have also double bonded over there or double bonded to the right. That is basically how you get to your resonance structures. And again, the real structure is probably somewhere between all the different resonance structures because those double bond electrons are basically moving around and delocalize. So here's an example of ozone. You don't have to worry about the charges on it, but ozone, you could double bond to the left, but you also have the option of double bonding ozone over there on the right-hand side. And again, those are 2 equivalent structures. If you're asked just to draw one structure of ozone, you could draw the left or the right one. They're both the same. Carbonate's the one we just drew. Again, we could have double bonded to the top like we did, to the left, or to the right. Benzene is actually an organic molecule. It's a ring structure. It looks something like this. Bunch of carbons and hydrogens, has 3 double bonds. Also, you can double bond it in the opposite way. And sometimes people will just draw benzene that looks like this with a circle to indicate that those double bond electrons are moving around. There's actually a carbon at each of these points. And there's actually a hydrogen attached to each of those carbons. And that's an organic molecule. If you take organic chemistry eventually, you'll draw a lot of benzene rings. We don't really do too much with it, but sometimes they use it as an example of resonance structures. So the last thing we're going to talk about here, I think today, here's another example of a resonance structure. We won't go over it, but you can look at it if you like. Are exceptions to the octet rule. So for our class, pretty much everything that you'll be asked to draw will obey the octet rule, which means everybody needs 8 electrons around it. But there are a few different exceptions to the octet rule that you do need to be aware of, although you'll never be asked to draw it, but you know, you will when you go to 1A, you'll draw a bunch of exceptions. But in here, we'll stick to following the octet rule. The first sort of exception to the octet rule is one that's referred to as an incomplete octet. And an incomplete octet is pretty much what the name sounds like. It means it has less than 8 electrons. And beryllium is an example of that, but really maybe doesn't exist so much, this structure. Boron is really the element that you come across the most in terms of an incomplete octet. So when you roll into 1A, probably boron is the most common example you'll kind of see with that. It is sometimes referred to as being electron deficient. It is perfectly fine with 6 electrons. And BF3 is an example. We don't need to add any electrons to it because it's boron. So typically speaking, if you look at the periodic table, which we got a lot of them in here, beryllium, boron, and aluminum are usually the ones that kind of fall into the complete octet. But really out of those 3, boron is kind of the only non-metallish type one that would do some covalent bonding. So that's usually your most common incomplete octet. So one exception to the octet rule is something like boron is perfectly good with less than 8. Another exception to the octet rule is one that's referred to as an odd electron molecule. And that is one where when you add up the total number of valence electrons, you hit an odd number. And basically what that means is it ends up having 1 unpaired electron, as we see here in these 2 examples. So you have 1 unpaired electron. Perhaps maybe you heard of free radicals. Those are things with like 1 unpaired electron. A lot of atmospheric chemistry. Chlorine has a lot of radicals in it of chlorine, and they're usually very reactive because frankly they have only 1 unpaired electron. They don't really want to be that way, so they oftentimes will react to sort of remedy that situation. But an odd number of electron pairs or an odd number of electrons is an exception. There are some that, you know, like NO or NO2 that can be that way. Probably the most common exception to the octet rule that you will see when you arrive in 1A, I know for sure, is the expanded octet. So that is a very, very common exception to the octet rule that you run across. Again, not so much in this class, but definitely when you roll into 1A. And there are certain elements that can actually go more than 8 electrons. So that is why it's referred to as an expanded octet. They can have upwards of 12 electrons around it. It's like 12 electron pairs, maybe 6 bonds, some bonds and electron pairs. And if you look at the periodic table, that is your friend sulfur. To the right, to the left, and down in the non-metal region, those are the guys that basically have the ability to go over 8. And that is because sulfur is located on period number 3, which if we remember from chapter 11, that is the n equals 3 level. And on the 3rd energy level, in terms of electrons, there are different orbitals. And on the 3rd energy level, we have s orbitals, we have p orbitals, and what orbitals also are there? D. That is the 1st energy level where d orbitals are found. And because they have the d orbitals available to them, even though they may not be using them, they have a place extra electrons, so they can accommodate the extra electrons because they have those those d orbitals. So anywhere on sulfur, left, right, and down that's a non-metal can technically go above 8. Yeah, I'll draw one in just a second. Now let's talk a little bit about the one above that on nitrogen, oxygen, fluorine, and that row. That is the 2nd period on the periodic table, which means n is equal to 2. On the second energy level, there are only s orbitals and p orbitals. They do not have d orbitals, which means if you have somebody that's carbon, nitrogen, oxygen, or any of those guys, they should never, ever go over 8 because they have no way of doing it because they don't have the d orbitals. So that's, again, an important thing to remember, probably more so when you get to 1A, to remember you should never go over 8 with anybody for sure, carbon, nitrogen, oxygen on that period. To answer your question, something like SF6 is an example of that. You can do the same thing. We would go S, and there would be 6 fluorines around it. And just kind of go around, and you do your bonds. That is 6 bonds to it, which means it has 2, 4, 6, 8, 10, 12 electron pairs. And to fill it out, all these fluorines would actually have dots around it. Now, they don't always have to be bonds that to go over the expanded octet rule. And since we're getting to the end, we'll do one maybe next time. But you could, I'll just use letters. You know, you could have something like this where, you know, you have 4 actual bonds. And you also could have just some non-bonding electrons on there as well. So what you would do is follow the same sort of process. You would make a single bond to everybody. You would still fill all the outside atoms with the dots and pairs. And then if you had leftover electrons, you then would go to the center and put the dots on the center atom, just like we did with all the other pictures. You just have a lot more dots, you know, on that central atom that could go, you know, upwards of 12 is pretty much the max. You could go 10 and 12 is usually where you can go in sort of the expanded octet. Any questions on any of that? Yeah. Yeah. Now, there, yeah, okay. We will then lay it up here for today, and let's talk about